Now we have the second presentation by Chukwudi Okeke. Thank you.
Thank you. Thank you, everyone. My name is Chukwudi Okeke. I'm a CAE engineer at YPAC, and I'm also a PhD student at Oxford Brookes University. Today, I'll be presenting one of my papers titled Modeling of Hyperelastic Polymers for Automotive Lamps under Random Vibration Loading with Proportional Damping for Robust Fatigue Analysis. No. Sorry for this. Okay, background. Premature fatigue failure of automotive lamp of polymers presents a big challenge in the design of automotive lamps. Currently, the lamp development is experimentally based. To reduce the product design cycle, there is a drive towards visual prototyping. There are challenges, though. Reliable input parameters, such as material models and manufacturing variability. Polymers exhibit hyperelastic behavior under deformation and are prone to manufacturing variabilities. Traditionally, the Rayleigh damping matrix used in the dynamic response analysis is constructed considering linear elastic behavior based on either initial stiffness or secant stiffness. To use a hyperelastic objective is to use a hyperelastic Mooney-Revlin material model to model random vibration response of components of an automotive lamp made of PCABS, PMMA, PPT40 materials. To compare the performance of linear and nonlinear stiffness-based Rayleigh damping matrix. Perform statistical analysis of response based on the Mooney-Revlin stiffness damping matrix. Random vibration response analysis. We are familiar with this equation. It's a dynamic response equation. And we're interested in damping matrix. It has widely been, linear model has been widely used in response analysis. But we understand that polymers are nonlinear. And modeling them with linear damping matrix, we present a huge error. So for linear and secant modulus, this is the damping matrix equation for the matrix. You have a tensile stiffness, and then we have secant stiffness. Secant is usually used when we consider the SNN curve nonlinear, but that doesn't really represent nonlinearity, if you like. So for nonlinear Mooney-Revlin model, damping matrix is given by this equation. And what happens here is that your elastic modulus varies with the stress-strain curve. Instead of taking one value that is constant at all strain, you have, because when your stress-strain curve is varying, the Young modulus is varying, dropping. So with Mooney-Revlin model, you follow the curve, and it's quite accurate if it matches the experimental curve. So we are interested. We need to estimate the damping, Rayleigh damping components, alpha and beta, and these are the equations for them. Now, the strain energy density function and the corresponding inertial stress for incompressible Mooney-Revlin, PCABS and PMMA, we used 3 parameters. And for PPT40, we used 5 parameters because it has huge nonlinearity. So you need to increase the parameters to match the stress strain curve. Specimens, that's experiment tensor test. So we need tensor test, we need the experimental data to determine. If we go back here, we actually need to estimate the parameters, moving parameters, to be able to get our stress. C10, CO1, C11. So we need to obtain them, and we need experimental data to do that. So here, our experimental tensor test. PCABS and PPT40 is a standard dog bones specimen, A1 dog bone specimen. And for PMMA, we cut the sample out from the plaque molded at YPAC. So testing performed under room temperature using Instrom 5582. Crosshead speed, 1 millimeter. The stress strain curve was measured using non-contact video gauge. The specimens were tested for 10 specimens were tested for each of the materials to measure the variability, the intersample variations. So we measured 10 samples. And for experiment for random vibration and damping, this is loading used for random vibration to test automotive lighting. And this frequency domain loading. And then here we have our schematic diagram of the test system, and then we have test setup. It's a cantilever beam test setup, basically. Okay, so specimen dimension is given, and the test specimen was mounted on a test fixture in a cantilever arrangement. The control and response accelerometer used were 3 for response. 353 BO3. The damping test was performed by sine sweep input from 5 Hz to 1000 Hz frequency, and 1G acceleration was used. 1 specimen was tested for random vibration, and 5 specimens for damping for each of the materials. And here is our experimental results. This is our stress strain result for PCABS, PMMA, and PPT40. We can see the PP40, can get the light. For PP40, we can see that it has a huge variation, intersample variation. And the nonlinearity is quite huge compared to other 2 materials, PCABS and PMMA. So I think PMMA appears to have smaller intersample variations. Okay? And that's the reason why we used 5 parameters to model PPT40, because of huge nonlinearity. And here we estimated the Mooney-Revin parameters I was mentioning earlier, C10, CO1, C11, C20, and CO2. And using the parameters, we constructed the stress. And then we compare the stress to the experimental stress. And then you can see the match there. So they're quite, they fitted very well, okay? So now we can use this, the elastic modulus of this Mooney-Revin model to do what? To model our response, to construct our damping matrix. And we did that. We constructed our damping matrix using linear and nonlinear, okay, Mooney-Revin, and tensile and secant modulus. This is the loading, input loading, which acceleration, it was the first loading I showed you, random vibration. It was, we converted the frequency domain data to time domain data. And then the acceleration versus time was also converted to force because of the mass, artificial mass, to drive the specimen. And I want to play that. I'm not quite sure. I think I might have to do that here, but you can see how. You can see how that is. That's the loading driving the shaker. Okay, so you can see that again if you want. Okay, let's see. And then we measure the response. Okay, and measure the response for linear and non-linear. Okay. Now, we see, here we go. This is simulation results. And for hyperelastic, we can see that the curve follows quite well with the experimental curve, compared to initial tensile stiffness and secant stiffness. So you have a good match for hyperelastic model. Why is that? Because it's non-linear model, so it's following the non-linearity, basically. So the elastic modulus is dropping as it should drop in real life, rather than having a constant value of tensile stress, why in reality it is dropping, and that is why. So it's a good match. And we established the error. Okay, we have a relative error, and you can see that the nonlinear hyperelastic has a very small error compared to others, which have very huge error compared to the nonlinear hyperelastic model. So that tells us that using linear model of either secant or tensile modulus to model our dynamic response for nonlinear materials such as polymers would give us quite large error. And it depends on the strain, how far you are going. So the further you strain it, the huge the error will be. Okay? So it appears to be a nonlinear material. Constructing the damping matrix with nonlinear material model seems to be a good approach. And here, now we've known that nonlinear model works, so we want to establish the variation. Okay? So what we did, we simulated 10 specimens that we tested, and then we established the upper and lower bound to see if experiments will fall within the upper and lower bound. And you can see it fell within the upper and lower bound quite nicely. So it's very good. That's for PCABS material, PMMA, and PPT40. And in conclusion, the random vibration response of PCABS, PMMA, and PBT materials have been successfully modeled using a hyperelastic Murray-Revlin material model. The performance of linear stiffness matrices is compared in this work with that based on the nonlinear hyperelastic Murray-Revlin model, specifically addressing the rate damping matrix construction. The hyperelastic model resulting in the reduction of the least square error at best by 11.8 times and at worst by 2.6 times. The Murray-Revlin model, material model, based the array damping matrix, was more accurate in modeling the dynamic behavior of components of nonlinear materials. The Murray-Revlin material model based the array damping matrix represented the manufacturing variabilities more reliably. The PMMA material was the strongest, which was the strongest of the three materials, had the lowest mean square error of the acceleration, followed by PC, ABS, and then PPT40 material. The materials with lower strength exhibited larger nonlinearity and the larger error in the dynamics response. That's what we saw for PPT40 material. Okay? And thank you for listening.
Thank you for your nice presentation. Maybe one short question or comment, because there is 1 minute left. No? We can start with the next presentation. You are...
Sorry, it's me again. So, okay. I don't know if I can give that somebody else just 1 second. So, does anyone want to take some photos? So, thank you. You know how to turn it on, don't you? Just here. Yeah, that's it. Thank you. Cheers. Okay. So the second one is it's a novel test rig for measuring bending fatigue using resonant behavior. Basically, this work came up because of the problem we had characterizing the fatigue properties of PC. We used tensor method to characterize it, and we couldn't. So we thought, how could we do this? Because we needed the properties to model our assembly. So, and then we came up with this method, which appeared to be very, very good and very efficient for us. So that's what I'll be presenting. So background, determining bending fatigue properties of polymer materials with the standard test systems is challenging, and in some cases, results are unattainable. This is particularly true of polymers that exhibit a higher level of nonlinearity and large deflection. Hydraulic and pneumatic mechanisms are the most commonly used load applications, although there are large drawbacks. Typical minimum rating force for servo-hydraulic is 5 kilonewton, and some polymers have lower peak force than 5 kilonewton. So it's a very, very big drawback. And for servo-pneumatic, it has lower loading force of it could go down to 1 kilonewton. However, it is not, because it is pneumatic, uses air, it is not stable. It is not, there is a very, very, if you have used it, you will see it's quite challenging to use it. Okay? And also the frequency is very, very low. So that means you're going to spend a lot of time, trying to characterize your fatigue properties. Okay? So quite a very big drawback, actually. So due to the compressibility nature of air, the operating frequency of servo-pneumatic is low, and the performance can be unstable. As a viscoelastic material, polymers are sensitive to test frequency and load amplitude. In some polymers, where viscoelastic effects are large, a notable temperature rise can take place, even at very low frequency. Okay. Objective: to develop a test rig for measuring bending fatigue properties using resonant behavior with the aim of characterizing the fatigue properties of materials that cannot be obtained with existing methods. Application of larger loads with small deflection by achieving larger acceleration. Reducing the time taken to obtain stress versus number of cycles to failure. It's an curve. Now, resonant fatigue test rig design. The design of the proposed fatigue test system uses similar support conditions to that of 4-point bending arrangement, resulting in a simple support. The loading is based on an inertia effect by having two double-sided small masses mounted on the test specimen. The total input force required to drive the system is the sum of the forces on the double loading masses, which is giving us this. That's the equation there. I don't know why there. Oh, yeah. So that's the equation. The maximum stress at the root of the notch. The notch is very, very critical in this work. It makes it to fail where you want it to fail. It's very, very good to have notch. So you know that there is no issue of stress concentration. So you know you are getting the pure material properties. And that's why notch is very, very important to use in this work. So the maximum stress at the root of notch is given as this. That's the maximum stress. And the KT is calculated using this equation here. So the normal stress, nominal stress start, and then the bending moment due to the applied force start. But that's a very simple approach, but it works very, very well. It works very, very well, and it's very easy to use. So we just validated it using FEA to validate it and see if what we are saying is actually true. Because it's very, very important for you to know before you start spending your time, making it, and then eventually see that, it fails. So here, we check the deformation occurred exactly where we expected it to occur. The equivalent stress, we thought it would occur at the root of the notch, and exactly that happened. Okay, we say, okay, we've practiced. This, this might be good. This will be good. Let's carry on. Okay. So we moved on. We did the tensor test to compare it with our new test setup. Okay. So and that is the specimen is PMMA. That's what we use to validate the system tensor test. And sorry. Here. So here is a specimen, loaded specimen, and that is a static jaw. This is moving jaw. So that jaw moves at 5 Hz frequency, okay? And then keep on pulling it until material fails. So the test carried out in accordance with the standard ASTM, and then the sinusoidal load waveform with frequency of 5 Hz. The levels of stress amplitude, 80%, 60%, and 40% of material yield stress were used to determine the SNN curve. The testing was conducted at the room temperature. So, experimental resonant bending. Here we use a rectangular shape. That's the geometry, which we introduced the notch. It's very, very helpful, as I said earlier. And then the resonant frequency of that specimen is 50 Hz. You can see the difference between 5 Hz and 50 Hz. So it's just very, very quick, 10 times what you would achieve. And we could not even achieve it even at that low frequency with the tensor test, okay, for PC material. Okay? So the specimen temperature was measured at every load. We tried to measure the specimen temperature because we had issue with the tensor test for this. And the loading was achieved by a inertial effect of 2 loading masses, as you can see it there. So we have that 2 loading masses there. Okay. And then we used the V721 electrodynamic shaker to excite the specimen. The testing was conducted at the room temperature. Here, that's a video which I would like to play. So you can see. Actually, wanted to start it a little bit. Yeah, it's going to be on. If it will, okay. It has. If you check, it should be the other direction. That's how I set it up anyway. But uploading it here has changed it, so you can see the speed anyway. So it's in the other direction, but it doesn't matter. You can see what's happening. Okay, that's how it is tested. Quite high, very, very large. You can see the speed. It's very, very, very good. Very good setup. It's very, 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 very good setup. Okay, so this is the result from it. So acceleration versus log number of cycles to failure. So we go from the system, the new system. And then we converted it to stress versus number of cycles to compare with the result from the tensor test. Okay? And you can see what happens here. They compare very, very well. The reason why we have lower stress for tensor is because bending stress is always higher. And for this, it's 1.25, higher than the tensor stress, and that's why you have, the resonance bending is on the top, okay? But they compare very, very well, okay, as you can see. So again, we now used it because as we have known that this works, so we used it to determine the fatigue properties of that PC that we could not determine using tensor test. Okay? Very simple, very easy. So what we found out and why this is the result from tensor test, we tried, we couldn't characterize it. You can see that's 80% loading here. That is 60% loading, and that is 40% loading. So it's very, very, very all over the place. It's not good. So it's almost at 40% loading, you get the same number of cycles as at 80% and at 60%. But that's not real. And why this is taking place? So we measure the temperatures and see the effect of temperature. So what we've seen here is that if you look at this is tensor test, and this is the ambient. Ambient temperature is 25.5, and at 80 increases to 37.2, okay? But 60 drops, and then at 40 it's almost equal to room temperature. And if you look at, before I move on, if you look at this 40, because temperature is dropped, it's actually the same as this, the same thing as that, because there is no effect of temperature, so we got the right property, okay? And so what happens here, we've thought that at 80% it's going to 37.2, so that softened the material. It made the material flexible, that it kept going, okay? It kept going, so then it went on to have a higher number of cycles, okay? Because of the temperature, made it a little bit softer, okay? So, but for resonant bending, something actually happened, that it became opposite. That if you look at here, ambient is 22.6. At 80, it's actually going down rather than going up. And why has that happened? If you do like this, I think it's called self-induced, okay, cooling. So if you do like that, you see that it kind of cycling in the air is just kind of cooling your finger, okay? And that's what actually is going on here. So it is cooling it as it is, you know. So you can see the higher the loading, the further it goes down. If you look at 60%, it's a bit higher because the frequency is lower, the acceleration is lower, okay? So the cooling is less. And then at 40%, the same thing, so it's almost equals the room temperature because the movement is very small. You see? So it's very, very good. In that case, it eliminates the effect of temperature. That even if you load it to the highest, higher stress, higher acceleration, it will actually be good for the specimen. It will cool it down. Rather than increasing temperature will be going down. So it's a very, very good system. And you can see very, very nice curve. It's very simple to use as well. Very, very simple to use. This will take you, within a day, you've done your work. But if I'm using the tensor test, I think to characterize this, if I'm using the bending or trying to reduce the frequency to be able to get this might take me the whole time of doing my PhD. Could take me 3 years trying to characterize only one SNN curve. Or a month, you know, it could take a long time. But this will do it in a day, 2 days, you know, get your properties and then model your system. Very, very easy, very quick to use. So, in conclusion, a novel test rig for bending fatigue test that is based on specimen resonant behavior has been developed. This novel test system setup support conditions are similar to that of 4-point bending arrangement. The loading is achieved by a natural effect of small masses mounted on the test specimen. A vibration shaker is required to basically excite the specimen at the first resonant frequency until it breaks. The time taken by the new setup to obtain SNN curves was 1/10, okay, of the universal testing machine-based approach. Okay? The fatigue properties obtained were comparable to the results based on the tensor fatigue properties. Furthermore, the test setup was successfully used to determine the bending fatigue properties of polycarbonate, of which determining the tensor fatigue properties with the standard test system was not successful. The specimen temperature decreases with increased load amplitude by means of self-induced cooling due to the specimen vibration, which eliminates concern of thermal failure. Thank you for listening.
Thank you for your nice presentation.